Hello everyone, this is Chen Zhang. I'm doing a demonstration for my course project of wireless communications. My project topic is a study and MATLAB simulation of a simple OFDM system for transmitting a piece of audio data over the frequency selective fading channel. Uh, First of all, I want to introduce to you the basic environment setup of my simulated OFDM system. Uh, well, the here you can see this is the basic structure of my simulated OFDM system. It's also the typical OFDM system widely used in wireless communication systems. Uh, in my system, I used n equal to 128, which means I have 128 orthogonal subchannels here, and at the transmitter, by doing inverse FFT, I generate the orthogonal substreams, and at the receiver, by doing FFT, we get back the 128 symbols. The modulation scheme used for each subchannel is 16 QAM, which is the most basic linear amplitude modulation schemes nowadays. And another important block is the cyclic prefix insertion. The length of the cyclic prefix insertion is said to be equal to the maximum delay spread of the fading channel. The transmitted signal is sent through the wireless fading channel, and at the receiver, we do a removal of the cyclic prefix insertion. And here is the 16 QAM demodulator. After demodulation, we get back the original high rate data stream. Alright, regarding the fading channel model used in my simulation, I used a frequency selective time non-selective fading channel, which is reasonable because multi-carrier modulation systems can effectively combat the frequency selectivity, not the time selectivity. Here is the discrete time impulse response of my simulated channel. It has the maximum delay spread of 10 samples, which is equal to my cyclic prefix insertion length, and each delayed pulses has the channel gain, which is distributed exponentially with lambda equal to 1. Okay, and here is the input audio data file used in my simulations. It's 16 kHz sampled and 16-bit encoded PCM file. Alright, and then let's run the program and analyze the results. Okay, the first I want to show you is the plot of 16 QAM constellation at the transmitter with equal distance. We can see that the signal points are positioned perfectly at their coordinates. Here is a plot of received signal constellation at the receiver. They experience the frequency selective fading channel and also the additive white Gaussian noise with some signal to noise ratio. We can see that the signal points are drifted apart from their original positions significantly. which means that the fading process and additive noise uh, introduce the change of amplitude and phase. Um, Here is another plot. This also shows the received signal constellation at the receiver. The difference is that this one does not. I do not introduce any fading process uh, for this one. So these two plots are obtained under the same noise power, but this third one does not experience any fading process. So we can see the influence of fading process. Okay, and here is the plot of symbol error probability versus signal to noise ratio in terms of EB over NR. The blue curve here represents the condition of fading channel, and the red curve here represents the condition of AWGN channel. We can say that the error performance under AWGN channel is much better than the error performance of under a fading channel, which is very reasonable. Uh, we can also say that it basically requires 10 dB better signal to noise ratio for the fading channel to achieve the same single error probability. Um, Another interesting issue to notice here is that here we can say as the signal to noise ratio increases, under my simulation setup, the symbol error probability gradually converges to a constant value, approximately 10 to the minus 5. Uh, I have not mathematically proved this, but I think this is due to the channel estimation method I used in my simulations. As I mentioned, before sending the actual data stream, I send some pilot symbols to estimate the channel attenuations for each subchannel. Uh, the the estimator I used to estimate the channel gain is the least square estimator. Uh, this is not optimal, but simple enough. The biggest problem for this estimator is that although it can effectively remove the fading channel attenuations, uh, but it also suffers from noise enhancement problem. So that my guess is that this is the reason that causes this irreducible error flow in my simulations. Okay, and I think if I use a better estimator for the subchannel attenuation estimation, this error flow can be eliminated. Okay, besides the symbol error probability versus signal noise ratio plot, another way to evaluate the error performance of my simulated OFDM system for transmitting audio data stream is to just plot the mean squared error between the recovered audio data and the original audio data. So here is the plot of the normalized mean square error versus signal noise ratio in terms of EB over NR. The mean squared error is computed between the original audio data and the recovered demodulated audio data, and then normalized by the average signal power. So here we can say once again the as the noise ratio increases, the normalized mean square error also converges gradually to some constant. This observation matches our previous results when we uh, discuss the uh, discuss the single error probability trend in this plot. And finally, this is a plot of the recovered audio data at the receiver under signal to noise ratio 20 dB. Alright, this is basically what I have done. Thank you for watching. Goodbye.